Every single day, millions of people get injections, vaccines, life-saving drugs, you name it. But have you ever really stopped to think about the insane journey that liquid takes before it even gets close to a syringe? It's this high-stakes, microscopic battleground where one tiny slip-up is just not an option. So yeah, let's dive into this hidden world. So what does it really take? Think about it. When you get a shot, that medicine is bypassing all your body's natural defenses, your skin, your digestive system, everything. It's going straight into your bloodstream. And that means there is absolutely zero tolerance for any kind of contamination. Perfect sterility isn't just a nice goal, it is the only goal. The real challenge here is this constant fight against an enemy you can't even see. We're talking about microscopic bacteria, viruses, even tiny dust particles. This stuff is literally everywhere. But inside that little glass vial, a single microbe could be catastrophic. And this is where the really cool science comes in. So how do they pull this off? Well, the answer is a brilliant technique called aseptic processing. What's so wild about this is that you can't just seal up the vial and then sterilize the whole thing, like you would canning food. Oftentimes, the medicine itself is too fragile for that. So you have to sterilize everything separately. The drug, the glass vial, the little rubber stopper, and then, and only then, bring them all together in this incredibly pristine, controlled environment. And you might think this is all just cold, sterile machines, but it's actually deeply human. The whole thing relies on these highly trained operators. They move with this slow, deliberate grace. Every single motion is carefully choreographed to avoid creating even a single stray particle that could contaminate the area. It's pretty amazing to watch. So let's talk about preparing that battlefield. To win this fight against contamination, manufacturers have to build what is, for all intents and purposes, a sterile fortress. We're talking about an environment engineered to be one of the absolute cleanest places on planet Earth. And the very first line of defense? It's the air itself. It is obsessively controlled. Now, just look at this table for a second. To give you some perspective, the air in a normal room probably has hundreds of thousands of particles floating around in every cubic meter. But in these critical Class 100 zones, the action level, that's the point where alarms start screaming, can be triggered by a single living microbe. It is thousands of times cleaner than the air you're breathing right now. So yeah, that means in the critical zone, right where the medicine is actually exposed to the air, the standard is nothing short of perfection. Air samples are expected to come back with zero contaminants, period. They achieve this with these massive HEPA filters, way more powerful than in a hospital operating room, and by using positive air pressure, which is constantly pushing clean air out of the room so nothing from the outside world can possibly drift in. And at the very heart of this fortress, you'll often find a piece of tech like this, an aseptic isolator. The best way to think about it is like a clean room inside of another clean room. It's a completely sealed off glass and steel box, a physical barrier that gives an even higher level of protection for the product, isolating it from pretty much everything. Okay, so the stage is set. The fortress is built. Now let's follow one single vial as it runs the gauntlet through the filling and sealing process. This is where incredible speed meets unbelievable precision. Before a vial can even dream of getting near the medicine, it has to be made perfect. First, it gets an intense washing with jets of ultra-pure water. Then, it's sent on a conveyor belt through this crazy hot tunnel that does two critical things. One, it sterilizes the vial, killing any potential microbes. And two, it does something called depyrogenation, which is a fancy way of saying it destroys endotoxins, these nasty fever-causing bits that dead bacteria can leave behind. Right? So once they're perfectly clean and sterile, the vials are automatically fed onto a conveyor and they enter that protected Class 100 critical zone. From this moment on, they will not be exposed to anything that isn't completely sterile. And here it is, the moment of truth. These filling nozzles descend and dispense the medicine. This is just a marvel of engineering. We are talking about dispensing the absolute exact dose, accurate to within plus or minus 0.5%. In a fraction of a second. The machine's even smart enough to know if a vial is missing, it just won't dispense. No vial, no fill. Then, immediately, and I mean instantly, after being filled, a sterile rubber stopper is pressed into the vial's opening. This is that critical seal. This is the moment the door to the fortress is slammed shut and locked, protecting that precious medicine from the outside world for the rest of its life. Okay, but what happens when the medicine isn't thin like water? A lot of modern drugs are actually these thick, viscous liquids. Think more like cold honey. And that presents a whole new set of engineering challenges. Right, so you can't just use the same pump for everything. For those thin, watery drugs, a standard peristaltic pump is perfect. It basically just gently squeezes a tube, kind of like how you'd squeeze toothpaste out. But for the thicker stuff, that's not going to cut it. You need to bring in the heavy hitter, a piston pump. It uses a really powerful vacuum to pull the thick liquid in before pushing it out. It's the difference between sipping water through a straw and trying to pull a thick milkshake through it. But sometimes, a drug is so incredibly thick that even a powerful piston pump struggles. So the engineers have another trick up their sleeve. They put the liquid into a pressurized tank and use sterile gas to literally push it toward the pump. But of course, that creates a new problem. All that pressure can make the filling tubes bulge out like a balloon, which would totally wreck the accuracy of the dose. So the final piece of this puzzle is special reinforced tubing that holds its shape under pressure, guaranteeing a perfect fill every single time. It's just brilliant problem solving. Okay, so the vial is filled, it's sealed. But how do you know? How do you really truly know that every single vial is perfect? Well, that brings us to the final gauntlet, a relentless series of checks and balances. At this stage, every vial gets scrutinized. You got high-resolution cameras acting like robotic eyes, scanning for the tiniest cracks or defects. You have checkweighers that confirm the fill weight down to the milligram. Sensors make sure the stopper is seated perfectly. And after all of that incredible automation, there's still a final failsafe. Every single vial is still visually inspected by a trained human being. But how do you prove that the entire process, the room, the people, the machines, the whole shebang, is truly sterile? You run the ultimate test. It's called a process simulation, or a media fill. Instead of the actual drug, they run thousands of vials and fill them with a nutrient broth, which is basically a perfect food for any stray microbes. Then, they seal them up and incubate them to see if anything grows. And here's the standard. This is what's amazing. For a typical run of, say, 5,000 vials, the number of contaminated units you're allowed to have is 0. Not 1, zilch. A single vial showing any growth means the entire process could be declared invalid. It can trigger a massive investigation and bring production to a grinding halt. The standard is nothing less than absolute perfection. And really, when you get down to it, this incredible safety doesn't come from just one single step. It's a comprehensive, multi-layered strategy. This pyramid here shows it perfectly. It's how everything, from the design of the building itself, to the equipment, to the operators, all builds upon each other to create this fortress of quality that guarantees the product is safe. So every day, this invisible battle is fought and won, all through this relentless precision and an obsession with getting it right. And because of that, millions of safe doses get delivered. It really makes you wonder, right? What other hidden, high-stakes processes are out there quietly making sure the world around us is safe?